Okay, hi, this is Ed Levin, Director of the Center on Addiction and Behavior Change here at Duke University. And pleased that you can come here for our third presentation of our Spring 2021 seminar series. And before I introduce today's speaker, I just wanted to look ahead a little bit. So next week, we're going to have, actually it's going to be the fourth week in a row we'll be meeting. And this is going to be Erica Bloom from the RAND Corporation is going to be talking to us about QuitBet, this digital social game, and it pays you to quit smoking, and then funded this work by a NIDA SBIR award. And then we'll be off for a couple of weeks, and then back on March 10th with Stacy Bilbo on her work with neuroglial interactions and inflammatory factors and substance abuse disorders. And then Kathleen Kanatak coming in later in the semester. Nicole Schramm-Cepeda from DIBS from Duke is going to be talking to her about her work with law enforcement in Durham County. And then finally, we're going to be having Isaac Lipkis from the School of Nursing talking about his work with water pipe smoking. Now I'm putting together the fall seminar series, fall 2021. So if you would like to present, or if you know somebody who would like to have them present, please send me an email, edlevin@duke.edu, or contact me. You can come by the lab or give me a call, and I'll do my best to arrange for them to be on the schedule. So now it's my privilege to present Dr. Brandon Henderson from Marshall University, and he is assistant professor in the Department of Biomedical Sciences at the Joan C. Edwards School of Medicine at Marshall University. He's been there, I believe, since 2017. And his area of research has to do with the neuropharmacology of addiction, which we'll hear about today. And actually has another line of work with neuroprotection and Parkinson's disease, which maybe we can get him to speak about another time. We actually have a pretty active Parkinson's group here at Duke University. And so today he's going to be talking to us about flavors enhance nicotine addiction related behaviors by altering ventral tegmental area neurons. Brandon?
Thank you. So let me set up my share screen, and while that's happening, I just want to thank you guys for having me. It's always great to be able to share your research, especially to be able to get some feedback. All right, so let me get my pointer set up. All right, everyone can see this?
Yeah.
All right. Thank you. Okay, so like Dr. Levin said, I'm going to be talking about nicotine-related events in the ventral tegmental area, and specifically regarding how my research has been studying flavors and how they exert some effects on the ventral tegmental area, and then that contributes to changes in addiction-related behavior. So just as a general outline, you know, one of the things I'm going to be talking about how in the nicotine field, vaping's changed the way that we've approached research. And really, my interest is, you know, so my background training is in chemistry. And then one of the things that's at least been interesting from my perspective is that vaping's introduced a number of novel chemicals that can then get into the peripheral and central nervous system. And then now we have new things that we can target and investigate in regards to behavior. So that's been interesting just from the neurochemistry perspective. So I'll talk about my research kind of in three arms. So flavors and their impact on reinforcement related behavior, on upregulation of receptors, and direct function on VTA, dopamine, and GABA neurons. So of course, we'll start with the background so we can kind of start on the same foundation. All right, so this is the information that pretty much, if not most of you, I would assume most of you would know. So one of the reasons why we're still interested in smoking is because it's the #1 cause of preventable death. Of course, you know, when it comes to obesity, that's getting close to being the #1 cause of death. So with smoking being at 500,000 deaths per year, and obesity, I believe, is getting close to 450,000 deaths per year. But still, smoking is consistently the #1 cause of preventable death in America. Tobacco products are responsible for a number of different types of cancer, lung cancer being one of the primary incidents. And then there's a lot of serious illnesses caused by smoke, whether it's firsthand, secondhand. Asthma is one example of that. And then, but the other issue is that of the people that do smoke, there's a large number, approximately 75%, that want to smoke but can't. And when it comes to the cessation agents, some of them vary in success rates. When you consider replacement or bupropion, Chantix, or even just the cold turkey sheer grit method, a lot of these may not work for certain people and different populations of American society. So still, this suggests the need for new interventions, and that used to be my field of research, not so much anymore, since I focus more on just the neurobiology of addiction. But just regardless, nicotine addiction is still a very relevant topic for research. But one thing that's changed is the advent of electronic nicotine delivery systems, or ENDS, as I will refer to them for the rest of the talk. So one of the reasons why, and I'll just skip to the next portion of the slide, that so many people are interested is just because there's some people are alarmed by the dramatic increase in use when it comes to youth as a entrance into nicotine intake. And for those of you that have kids, I myself have very young kids that aren't, they're 2.5, so I don't have to worry about them smoking. But eventually they're going to be at the age population where this may be a risk factor. So this is another reason why I'm interested, just because at this point we don't really know the health consequences of vaping. We do know that it can contribute to increased risk for stroke, but really it took a long time to determine the health associated risks of combustible cigarettes. It'll take time for vaping, but it's still something that we need to consider, especially since the unique factor about vaping is that less than 5% of those people that vape use an unflavored products. And so to put this into context, even if you have a tobacco e-liquid, usually that still has characterizing flavors. But this provides a new area of questions, because when it comes to these chemical flavors being used via an inhalation route, it provides rapid entry to the brain. So there's a lot of questions about what these chemical flavors and odors may be doing to behavior. And that's actually one of the things that I've been working on for the past few years. So just to kind of complete the discussion, there's a lot of distinct varieties of vaping devices. When it comes to anything a person may have used to smoke, they've now made an e-version, so they even have e-pipes, e-cigars. They have a large tank systems, which are you can customize the e-liquid. But then there's a lot of closed loop systems. So basically what you buy, you can't really alter unless you get some after or off market products. But the most popular one still, even after some of the recent restrictions, is the Juul or different pod-based systems that are interchangeable. They're small and they're easy to hide, which makes it really popular for, at least in my area, middle schoolers and high schoolers to hide from their principals and teachers, etc. So for people that are nerds about nicotine, one thing that's been interesting about comparing combustible cigarettes to tank-based or pod-based vaping devices is the difference in nicotine content, which may provide some different pharmacokinetic values. So when it comes to combustible cigarettes, there's a range in milligrams of nicotine per cigarette. When it comes to tank-based systems, there's a lot of variation, just because you can go to some shops and they have a coffee house type of mentality where you can ask them whether you want it weak or strong, and so they can, and at least in West Virginia, I've seen that they'll customize the e-liquid for you. But you can purchase things anywhere from 0 up to 24, 3 to 16 milligrams per milliliter is very common. And one thing with many of the tank-based e-liquids, they're using nicotine freebase as the formulation, but Juul was unique in the fact that it used a nicotine salt. But because of the popularity of Juul, there's more e-liquid companies that are using nicotine salts as opposed to nicotine freebase, which scientifically is interesting because it brings the question, what may formulation do when it comes to behavior? And we'll talk a little bit about that later. Okay, so like all drugs of abuse, that alter the dopamine signaling system. Nicotine does so. And the one way it does this is there's a lot of high density, high affinity nicotinic receptors in the ventral tegmental area. So nicotine will bind these receptors, cause receptor activation, contribute to dopamine release, and then you'll get the feel-good sensation. So that's one way that nicotine controls reward signaling. But to be more specific, so it does this through nicotinic acetylcholine receptors that many of us know. They're pentameric, they're ligand-gated ion channels, and they come in different varieties. The two primary types being heteromeric and homomeric, with the homomeric are largely known as alpha-7 and alpha-9 receptors, whereas the heteromerics are combinations of alpha-2 to alpha-6 and beta-2 to beta-4. When it comes to some of the earliest connections between nicotine use and nicotinic receptors, one of the first understandings that have come from scientific investigation was that beta-2 containing nicotinic receptors are upregulated in humans, rodents, and cell lines. You can also knock out a beta-2 or an alpha-6 or an alpha-4, and then rodents will fail to self-administer nicotine. You can then selectively re-express them in the ventral tegmental area by itself, and then that will rescue the function of self-administration in those rodents. You can also selectively activate an alpha-6 or an alpha-4 nicotinic receptor subunit, and these will be sufficient for condition place preference. So anyways, so this is all saying that nicotinic receptors are important for nicotine reward, and it may be these receptor subunits that are very critical for at least the initial stages of nicotine reward and reinforcement. So being a basic scientist, I don't study human brain imaging. I don't study human neurobiology. So basically, my functional correlate is a mouse brain. And specifically, I'm interested in the dopamine neurons that project to the nucleus accumbens. And so what prior science has taught us about nicotine's actions is that there's a balance of inhibitory and excitatory tone in the ventral tegmental area, where GABAergic neurons will inhibit dopamine neurons that both have nicotinic receptors on cell bodies and terminals. An acute application of nicotine, so smoking relevant concentrations will be between 0.1 to 0.5 micromolar or 100 to 500 nanomolar. So those will acutely activate these nicotinic receptors, creating a net positive dopaminergic tone, increase in dopamine release, and then initial stages of reward. So when it comes to long-term applications of nicotine, you'll have upregulation of nicotinic receptors on both of these cell bodies, on the GABA neurons and the dopamine neurons, but it's more selective, or there's a higher degree of upregulation on these GABAergic neurons. So what this means is you have enhanced inhibitory tone onto the dopamine neurons, and this is one of the things that may drive craving. So essentially, these dopamine neurons are inhibited to a higher degree. Then, in the presence of acute nicotine, what happens is you'll have both of these systems of nicotinic receptors activated, but the GABAergic neurons have alpha-4 beta-2 receptors that are essentially inhibited, or that are desensitized and turn off, and then the dopamine neurons are disinhibited, driving a greater outflow of dopamine, which then drives reinforcement-related behavior. And this doesn't come or put into play the local VTA glutamate neurons that then provide excitatory tone. But regardless, the dynamic of disinhibition on dopamine neurons is one of the principal mediators for the continued reinforcement of nicotine. All right. So at the very beginning, I mentioned that flavors are an interest of my lab, and they've been what I've studied for the past few years. So essentially what got me into this field was just the knowledge that when it comes to combustible cigarettes, there's still a third of smokers that primarily use menthol cigarettes. So as an African-American, I was interested in the fact that pretty much every African-American smoker uses a menthol cigarette, but then also these people have a lower success rate when it comes to quitting. And the thing that kind of like made me a lifer when it comes to studying flavors is a study that came out by Arthur Brody in 2013, where he looked at human brain imaging comparing regular or unflavored cigarettes versus menthol cigarettes, and he saw a greater degree of upregulation in human brains. So essentially at the same time, and even slightly before that, there are studies that show that menthol could directly act on nicotinic receptors, mostly through mechanisms involving negative allosteric modulation and non-competitive inhibition. So that's when I first became interested in menthol and its role in nicotinic receptors, and hence why we're going to talk about flavors and first how they impact behavior, and then I'll follow up with the impact on the receptors, and then on the impact on the neurons themselves. Okay, so now we're going to talk about our behavior. So first I want to explain our current system, which is using a vapor self-administration system. So those of you that are familiar with nicotine IVSA, this is trying to be similar, but using a vaping relevant model. So essentially we're using vape tanks that you could purchase off the street, but we stick to what's called a SMOC baby beast just to be consistent. Basically, there's a negative pressure system driven by a compressor that pulls air continuously. Once the mice nose poke on the active side, they'll get a 3-second delivery of whatever e-liquid we have them assigned to. And we also track the inactive nose pokes just to make sure we're actually learning the behavior and it's not just a random nose poke. So we've had different ways of training that we've tried over the past 2 years to get this a little bit more robust and consistent. So essentially what we first attempted to do was just free escalation on an FR1 schedule, so fixed ratio 1 nose poke, 1 delivery over a 10-day period, and then transition them to a fixed ratio 3, so 3 nose pokes, 1 delivery. That typically got about a 30% success rate for males and a 25% success rate for females. So that wasn't very consistent and not very robust. What we eventually got to was a training regimen where we would train them for 3 days with just strictly non-contingent exposure. And the explanation for that was we've noticed that the mice are basically, they may be, whether it's a fear-related phenomenon or if it's just an aversive stimuli, basically they needed to get used to the vapor cone delivery. So we did 3 days of non-contingent exposure, and then basically we did a training wheel approach. So the first 3 days, they would get a non-contingent exposure if they chose not to nose poke within an 8-minute interval. And then basically we weaned them off of that, and then they were freely escalating, hopefully over the span of 10 days, and then transition to a fixed ratio 3. So with that training method, we've got to about a 66% success rate. So that's about 70% for males, and then anywhere between 50 to 60% for females. And that's for adults and adolescents. And right before the pandemic started, we were transitioning this from basically, instead of going straight from FR1 to FR3, we'd put an FR2 schedule in between. So that got disrupted with the pandemic, and we're just now getting to the point of evaluating if this will enhance our acquisition rates. So the first thing we did was we actually bought commercial e-liquids, and I'll explain that there's definitely some pros for translational applicability. There's definitely a lot of problems with this because at the end of the day, commercial e-liquids, you can get the same bottle 3 times and you can get a completely different e-liquid flavorant ratio or nicotine content with each one of those bottles. So there's definitely problems with that. So in this experiment, we're looking at training the first 10 days of FR1 with menthol and nicotine, green apple by itself, the vehicle, which was propylene glycol, vegetable glycerin at a 30-70 ratio, green apple plus nicotine, and the nicotine by itself. And all of these nicotines are 6 milligrams per milliliter. So basically what we saw is that first we did a Q-light only control group, and then the mice would respond on the first for that, but then essentially they would be uninterested in cue light stimulation only. So nicotine, they would acquire the behavior, not so much, but when it came to the flavors, whether it was green apple plus nicotine, green apple by itself, or menthol plus nicotine, they escalated at a much higher rate. And I'll mention that menthol by itself, the mice didn't escalate on that, and I didn't show it on the graph just because it's a little busy down here. And then they pretty quickly became uninterested in the inactive nose poke side. I will mention that we've changed the PG-VG ratio. That has changed the ratio between active and inactive, but unfortunately we still have a low end, so I'm not going to go into that in any detail. So once we trained them for 10 days on FR1, we transitioned them to a fixed ratio 3. So just as a reminder, 3 nose pokes get 1 delivery. So here we used nicotine, green apple plus nicotine, menthol by itself, and menthol plus nicotine. So here what we're seeing is that green apple by itself, the mice will self-administer that. And if you add flavors to nicotine, you have a significant increase in reinforcement-related behavior. To show that this is at least partially mitigated by a nicotinic receptor mechanism, we use the nicotinic receptor antagonist DH-beta E immediately prior to their vapor self-administration sessions. And so when it came to nicotine, we could completely block self-administration, but we can only partially do that when it came to green apple plus nicotine or nicotine plus menthol. So suggesting that this was certainly due to a nicotinic receptor mechanism and partially so for the flavors. So the one thing we did next is I mentioned the problems with using commercial e-liquids. So since then we've transitioned to the e-liquids we use in the lab are only ones that were made in-house. So we basically purchase research grade nicotine and chemical flavorants. We mix them ourselves to match ratios that have been published due to analytical chemistry reports on e-liquid compositions. So here we're just showing an example of nicotine plus menthol training, just to show that with adults and adolescents, in this case it's males, they self-administer and increase their FR1 acquisition rates in similar manners. But I just wanted to highlight with the adolescents, we've consistently seen they kind of go through these binge-like behaviors where they get to a point where they'll have a high day and then a low day, and that kind of alternates back and forth. So that's something that was interesting. We're probably going to follow up on. So I also wanted to note or to highlight the fact that you can see a clear difference in the e-vape deliveries with the liquids we've made in-house versus, and I'll go back, versus the e-liquids that were commercially purchased. So using a similar model, we can get the same exact trends with the in-house made e-liquids on a FR3 schedule. So green apple by itself was self-administered to a similar degree to nicotine by itself. And then we would add flavors to nicotine, and we had a significant increase versus nicotine by itself with green apple and menthol. So we've also have done a few dose response studies where we would train the mice on 6 milligrams per milliliter nicotine, and then use it within subjects' design for cycling through different concentrations of nicotine. And with male mice, so far we've seen that 6 milligrams per milliliter is preferred. The caveat is that this could just be a preference that's been established with their training. So this is something that we're gonna repeat in different ways just to make sure that this is a valid dose response curve. Okay, and just to finish this off, so we did a similar study where with the in-house made e-liquids, if we give DH-beta E, can we confirm it's through a nicotinic receptor mediated mechanism? So once again, nicotinic receptor antagonist DH-beta E was added prior to the self-administration sessions, and we could block reinforcement related behavior for nicotine, green apple by itself, green apple plus nicotine, and menthol plus nicotine. And the last thing I'll show you is that we have had some success with doing a progressive ratio, but that's only with the e-liquids that have nicotine plus flavors. essentially that basically, and it's also a very low schedule. For those of you that may do IBSA, you'll see that the schedule is pretty low for the progressive ratio, but that we have had some success in looking at motivation-related behavior with this assay system, and it produces the trend that's very similar to the FR3 delivery. So green apple was self-administered, similar rates to nicotine. You add green apple to nicotine, you get an enhancement. In this case, it's not significant versus nicotine. Menthol plus nicotine was significant versus nicotine. So it's been consistent as far as trends, whether it's a FR3 or progressive ratio. Okay, so some of the things that we keep learning when it comes to vaping products is that, so I mentioned at the beginning that there's a lot of novel chemicals that are coming into these vaping products. And one of the things I've been learning about recently is a nicotine alkaloid called nicotyrene that tends to show up in vaping e-liquids just due to chemical reactions and dehydrogenation with intermediates that are produced either by heat or just oxidation in PGVG. So these are some interesting papers that hopefully they'll be of interest to you, but it's basically shown that over time in e-liquids, just by the process of opening and closing the bottle, you can produce certain concentrations up to 20% of nicotyrene in the e-liquid, and this compound will reduce the metabolism of nicotine, so essentially producing higher plasma nicotine for a longer period of time. And then also we've shown in our electrophysiological studies that I won't discuss in this talk, but this is a partial agonist of alpha-4 beta-2 and alpha-6 beta-2 containing nicotinic receptors. So backtracking to the commercial e-liquids we've had, so we found out with preliminary analytical chemistry, our e-liquids at the time of the experiments had approximately 10 to 15% by weight of nicotine, nicotyrene. So that may have been impacting our behavior studies. And that's one of the reasons why I pointed out the different numbers of deliveries with the commercial e-liquids and the in-house e-liquids. But this is another interesting thing that needs to be followed up when it comes to the vaping-related behavioral assays. Okay. So I also mentioned before that when it came to these products, there's a difference between, the presence of nicotine salts and the presence of nicotine freebase. And basically, we also have the question, so how does a salt or freebase formulation impact reinforcement-related behavior? So recently, I did that experiment by simply training mice with the identical e-liquid. So in this case, since mice have had the highest acquisition rate with nicotine plus menthol, that's become our actual training regimen. So we'll train them on nicotine plus menthol because we get the highest rate of acquisition, and then we'll transition them. In this case, we transition them to nicotine freebase or a nicotine salt, in this case, dihydrate ditartrate, and then basically compare the two using a within subjects design. So the same mice gets all of these e-liquid assignments. So how does freebase formulation compare to the salt formulation? What we saw in both males and females, mice assigned a nicotine salt, self-administered more compared to the freebase. And one of the reasons this may be the case is because the mice assigned nicotine salts had a higher plasma cotinine value. So I know that this isn't directly measuring plasma nicotine, but let's just assume that cotinine is a direct or indirect way of measuring plasma nicotine. And so the assumption is that more nicotine may be delivered with the salt formulation. So this is something that's still preliminary, and we're still, this needs more investigation. And by that, we need to do some direct nicotine pharmacokinetic studies. Okay, so most of the upregulation in electrophysiology data that I'll show you is from mice that have been through condition-place preference assays. And that's simply because it's taken us so long to get our self-administration system up and going. We haven't yet got to the point where we're just now getting to the point where we do the self-administration and then we do the follow-up neurobiology and neurophysiology studies. So up to this point, we've basically done condition-placed preference and then taken those animals and done neurobiology and then electrophysiology. So just as a brief primer, most of you probably know this, but condition-placed preference is a model where you allow a mouse to establish a preference in a chamber. You can give nicotine, or in this case, nicotine plus flavors or flavors by themselves in one chamber, saline in another, and you can study their change in preference, and basically moving toward or spend more time spent in the drug paired chamber is indicative of reward, and the reverse is indicative of aversion. So just to show one of our older studies that's been published for a while, menthol by itself didn't show any reward related behavior. That was something that we expected given some of the prior literature that came out. But if you combine nicotine at a non-rewarding or rewarding dose, combine it with menthol, you get an enhancement of that behavior. And we know it's an enhancement because menthol by itself did nothing. So that's to kind of set the stage. And since we're studying flavors, we then transition to two individual chemical flavorants of green apple. And to answer the question of why green apple, well, when it comes to vaping, menthol for a long period of time was the king or the #1 choice of vaping enthusiasts. Green apple was the #2, but now green apple is actually one of the top flavors for usage. So we started with two different chemical green apple flavorants. Farnesol is one, farnesene is the other, and then here's their chemical structures at the bottom. So using condition-placed preference, we notice a sex-specific effect with farnesol in adult mice. So essentially, male mice would show reward-related behavior at a dose of 1 mg per kg. Female mice did not. And then also with the male mice, if you use DH-beta-E, you can block the reward-related behavior, showing that this is likely through a nicotinic receptor mechanism. So in the case of farnesene, we saw that farnesene would cause CPP at a single dose, 0.1 mg per kg. But in the case of females, it's sex-specific, but in the fact that there's a broader range of doses that were significant versus saline treatment. All right, so using those condition-placed preference studies, we then followed up with upregulation and electrophysiology. But first, I'm going to talk about what we saw looking at upregulation of nicotinic receptors. So just a very quick primer on what some of us believe is happening with upregulation. So there's been a lot of studies that have shown that nicotine potentially gets inside cells and neurons. And once it's inside cells and neurons, it can aggregate into the endoplasmic reticulum. It can enhance the formation of receptors due to stabilizing dimers and trimers, which then increase the rates of pentameric formation. But that impacts the secretory machinery and deposits more receptors onto the plasma membrane of neurons. So the important thing is that once on the neurons, these upregulated receptors are different in their formation or their stoichiometry. So for example, alpha-4 beta-2 receptors exist in two different stoichiometries, but nicotine will stabilize the high sensitivity form. And there's a question about alpha-6, alpha-4 containing receptors, and that's complicated. And from my experiments, my belief is that it's region specific. So one thing happens at the cell body, and at the terminal, something happens that's different, but I don't have time to go into that. So the strategy we use is something that was established by my postdoctoral mentor at Caltech. So we've generated knock-in or transgenic mice with fluorescent nicotinic receptors. So these are using GFP, mCherry, or YFP. We can expose them to nicotine. So right now, we're mostly using the vaping model, but for the purpose of the rest of this presentation, it's condition-placed preference. So we can basically isolate the brain tissue, use it in any way that we want, and follow up with investigations. So as I mentioned, this was pioneered by my postdoc mentor, and there's been several papers and several mice lines that have been produced. The one I'm going to focus on is this one that I myself made while I was still a postdoc. So we're interested in the ventral tegmental area and other similar regions of the midbrain. Typically, we'll use this mouse to cut coronal slices so that we can see the VTA, the SNC, the SNR, in some cases the IPN. And then we can use fluorescent measurements to study changes in receptor numbers. So the one thing I'll mention is hopefully pretty soon these mice will be in the on the MMRRC for use for anybody that wants them. That was another thing that got delayed by COVID, but hopefully sometime soon those will be available. So using these mice and just vanilla confocal microscopy, we can do specific studies with alpha-6 containing receptors, alpha-4 receptors, or receptors that have an alpha-4 and an alpha-6. To do this, we use FRET-based methods where we can basically confirm which regions have these two receptors that are basically physically touching with each other. Okay, so my menthol study was published years ago, so I'll just summarize that right here. So when it comes to nicotine by itself, nicotine will upregulate alpha-4 beta-2 receptors in the tail of the VTA, and depending upon dose, you'll get upregulation of receptors on dopamine neurons, but it's dependent on dose and it's dependent upon exposure time. But in the case of nicotine plus menthol, what'll happen is that the degree of upregulation is increased by 25 to 30% on GABA neurons when it comes to alpha-4 beta-2, and then you'll have a consistent increase of receptors on dopamine neurons. And the thing I'll mention is that in the case of the alpha-4 beta-2, it had the exact degree of enhancement that Arthur Brody saw in his human brain imaging study. So it's always nice when different types of experiments can agree on certain data points. So that was very affirming when I found that data. Okay, so the question is, what about green apple flavor? So here I'm starting with just farnesol, and what happens with the upregulation in VTA dopamine or VTA GABA neurons? So there's a lot of data, so I'll just take you through it slowly. So chiefly what happens with alpha-4 containing receptors on VTA dopamine neurons, what we saw is that essentially nicotine did what we've seen before, upregulate. Farnesol did not significantly upregulate. So basically there's no effect there. Nicotine plus farnesol had an effect, but follow-up experiments showed that this effect was mostly nicotine. So farnesol largely doesn't have an effect on alpha-4 containing receptors. So uniquely, farnesol would upregulate alpha-6 containing receptors, and this is unique because nicotine does not do that, especially when it comes to doses that are consistent for condition-place preference. So jumping down to the VTA GABA neurons, one thing that was interesting was that nicotine will consistently upregulate these receptors. Farnesol plus nicotine kind of reversed that effect, and when farnesol was applied by itself, it actually downregulated these nicotinic receptors on these GABA neurons. So essentially, just in summary, there was a somewhat selective effect on alpha-6 receptors on dopamine neurons, that being an upregulation, but then there's a downregulation of alpha-4 beta-2 receptors on GABA neurons. And this will make more sense once I talk about the electrophysiology, because we see something that parallels that. So, and I'll mention that, so just like we saw a sex-specific effect in CPP, we saw a sex-specific effect on upregulation. So this is what happened with male mice, and we didn't see an effect with the female mice. So switching to the next green apple flavor, farnesene, essentially, long story short, in the VTA, dopamine and GABA neurons and the SNR, we actually saw no effect when it comes to upregulation for males or females. And we'll talk about this in a little bit, in a few more slides. So now moving on to how these flavors may be changing the function of VTA dopamine neurons. So before I do that, I'm just going to give a very quick primer for those of you that aren't daily electrophysiologists. So essentially what we're doing with these experiments is we're utilizing the fact that neurons are chemical and electrical in nature. So there's several ways of studying these type of properties. One being electrophysiology, one being electrochemistry. But one of the things that we're chiefly interested in when it comes to these dopamine neurons is the transition between tonic and phasic firing patterns, because the phasic firing patterns is one of the things that may be a good indicator for addiction-related behavior. New data is showing that may not be the case, but it is definitely showing transitions from low to high activities of VTA dopamine neurons. So here's an example of an electrophysiology setup. So when it comes to brain slice electrophysiology, we can visually identify the neurons. And one of the extra benefits of our fluorescent nicotinic receptor mice is that we can identify neurons that have specific nicotinic receptor subunits and then target them for our electrophysiological investigations. So I'll mention that our alpha-6 GFP subunits are an excellent marker for dopamine neurons because they have a 95% overlap with tyrosine hydroxylase. So basically, 95% of the alpha-6 GFP positive neurons are also dopamine neurons. And so those are just examples of some of the imaging. All right, so here we have a sample image from our actual one of my brain slice experiments. So we can use alpha-6 GFP to identify a putative dopamine neuron for patching. And so just at a baseline, we're looking at farnesol, one of the green apple flavors, and just how does that affect baseline firing frequency. So what we saw that in male mice, farnesol will increase baseline firing frequency of VTA dopamine neurons. So this was another sex-specific effect. So we saw this in males, excuse me, but we didn't see this in females. So this is another point that, different data sets are agreeing. So with the CPP, the neurobiology, and the electrophysiology, we observed a sex-specific effect. So that was very confirming. So baseline firing frequency will tell us one thing, but what we're really interested in is what happens when nicotine is on board. So using a similar setup, we're patching onto VTA dopamine neurons, and then we apply nicotine at 0.5 micromolar, and we do that for a 10-second application. And then we study the increase in firing frequency. So essentially what we saw is that in the baseline state, we'll have a non-significant increase of firing frequency. In the case of mice treated with farnesol, at the baseline state, we have a significant increase in firing frequency, but then we apply nicotine and we have about almost a twofold increase in the firing frequency. That is significant. And just to be sure, if we apply farnesol by itself, and we did this up to a concentration of 1 micromolar, farnesol does not change firing frequency by itself. Also what's happening with the GABA neurons. So I mentioned before that we saw a downregulation of receptors in the VTA GABA neurons. So one thing that isn't shown here is that at the baseline state, if we compare saline to farnesol treated mice, they have a significant decrease in the baseline firing frequency of their GABA neurons in the VTA. So when we add nicotine, we'll have an increase with the saline treated mice. This is also not significant, but we'll still have a significant increase in the firing frequency of the VTA GABA neurons. So farnesol, even though it's decreasing the baseline firing of GABA neurons, it's still facilitating a greater transition to a higher firing frequency. And VTA GABA neurons are also unaffected by acute farnesol treatment. So essentially, if we're comparing the network of inhibitory to excitatory neurons that project to the nucleus accumbens, one of the things we're seeing is that the firing frequency is decreasing these GABA neurons, but increasing these dopamine neurons. And part of that goes with each other. So the reason why these dopamine neurons are firing at a faster rate is partly due to the fact that they are receiving less inhibitory tone from these GABA neurons in the VTA and the tail of the VTA. Okay, so that was one of the green apple flavorants. So what about the other? So now we're looking at farnesene, and what we saw was something distinctly different. So farnesene did not change firing frequency, so I'm not going to show that. But what it did do is change the perceived potency of nicotine on these neurons. So it's a similar setup. We're patching VTA dopamine neurons, and instead of measuring action potentials in current clamp mode, we're actually applying nicotine at different concentrations to look at inward currents. And so a untreated or saline treated mouse will have a concentration response of nicotine but the mice treated with farnesene had a leftward shift. So basically at lower doses, we're getting higher peak current amplitude and a perceived change in the potency of these receptors. So this is suggesting that farnesene is actually, while it's not upregulating, because if you recall, farnesene did not upregulate any of the receptors or male or female mice, despite the fact that it caused CPP on its own. But what it may be doing is changing the stoichiometry of nicotinic receptors so that more of them are high sensitivity. And so we did the follow-up experiment. So using a very simple FRET experiment, these are cultured neuro-2A cells that are transfected with alpha-6 or alpha-4, alpha-6, beta-2 receptors, or alpha-4, beta-2 receptors to look at different stoichiometries. So we'll focus on just this side. Different stoichiometries of alpha-4, beta-2 have different FRET values. So the low sensitivity having 3 alpha-4s, and if we use the M-Cherry, that's basically 3 acceptors. So it's more energy that they can accept, so they have a higher energy state. So what happens if we do a FRET experiment, and if the energy goes down, what that means is we have more of the receptors that have less acceptors. So this would be a high sensitivity receptor since it has more beta-2. So that's what we saw. So we added farnesene. We saw a decreased number of FRET events and a decrease in FRET energy. So this is suggesting that farnesene by itself will change the nicotinic receptor stoichiometry so that it has more stability of the alpha-4 beta-2 in the high sensitivity form. So also to look at different changes in sensitivity, one of the other things we can do is just looking at spontaneous excitatory postsynaptic currents. And so the way we do that is with the VTA dopamine neurons we're studying, we have excitatory and inhibitory inputs. So remember, these are, so which I haven't said that these are coronal brain slices that I'm using for patch clamp electrophysiology. So the excitatory inputs are mostly local glutamate neurons. The inhibitory inputs are mostly the local GABAergic neurons. So you can add an antagonist to block these inhibitory responses and selectively study excitatory responses. So if we do that and we compare saline to farnesene treated mice, we can see that we have an increase in excitatory postsynaptic current. So this could mean there's more excitation, or it could just mean that it's indicative of a change in affinity. So similar levels of stimulation just provide a bigger net response. So I will say I haven't followed up on seeing if there is a change in excitatory input, but this is still showing that farnesene is creating a change in the frequency of events and also the amplitude of events. So last thing is that farnesene by itself seems to be acting as a partial agonist. So here we're doing similar studies with patch clamp electrophysiology on brain slices, adding concentrations of farnesene, which I'll admit these concentrations are much higher than what would be vaping relevant. We expect the concentration to be less than a micromolar when it comes to brain level exposure. But at high concentrations, farnesene does cause inward currents that are blocked by DH beta E, showing that this is likely due to a nicotinic receptor mechanism. So just to do a comparison to nicotine, we can see that at the highest concentration, it's maybe 45% the efficacy of nicotine on a VTA dopamine neuron. And also I'll mention that I've repeated these experiments on cultured cells and showing that it works, or this happens on alpha-4 beta-2 and alpha-6 containing nicotinic receptors. Okay, so just to summarize, the one thing I hope that came across is that the flavors by themselves, they can enhance nicotine-related behavior. They can enhance self-administration, but one thing I want to highlight is that the green apple flavors seem to be able to do this by itself. So the green apple flavors could cause self-administration. They can also cause CPP by itself. So the flavors also change upregulation. It's complicated, and we've only looked at one region of the brain, that being the midbrain. So there's a lot of other things that need to be understood when it comes to upregulation. But upregulation seems to be tied to dopamine and GABA neuron excitability, and we saw that change. And we believe this is one of the reasons why there's a change in reward and reinforcement related behavior. Essentially, just the flavors are altering this pathway, and that seems to be one of the primary reasons why they're impacting behavior. Okay, so that's what I have for today. So I want to thank my lab. So basically, the people that were did some of the experiments are highlighted in black. So sadly, they've moved on and are on to bigger and better things. But my primary graduate student is still involved, and we have a good system where they do a lot of the behavior, well, half the behavior, all the microscopy work, and that allows me to do all the electrophysiology. And also I have great kids, and they provide my moral support. So I guess at this time, if you guys have any questions, I would love to answer those questions.
Okay, I wanted to thank you, Brendan. That was just stellar. I mean, wonderful presentation, great batch of work, and raised a lot of questions. I just want to let people know we'll have some direct questions for the next 8 minutes or so to 1, and then I realize some people have to sign off, but we do have an hour of extended discussion. If anyone wants to stay on the Zoom, we'll have some informal discussion after that. So I just wanted to start off with just an overall question about green apple. Menthol we've known about for decades, and it's been a big part of the tobacco addiction out there. Green apple just seems to have come up with the e-cigarettes. I mean, is there an idea of, is this a recent discovery, or I mean, that's been around for a while, or what?
I don't know if it's recent, because before combustible cigarettes were just menthol, I remember, so I have older family members that so they're now like menthol smokers because that's the only option they have, and they're like, they see themselves as too old to be vapors. And so they would have like what there is this it basically smelled like a Jolly Rancher version of a cigarette, and they would that was their go-to for smoking. So I think it's one of those things. I mean, different people have different flavor preferences. Like my wife, she loves green apple everything. I'm not a fan, but if she was a smoker, it would be green apple. So I think it's just one of those things. It's like there's humans are very unique and very varied, and so there's something for everyone. I think that's what's unique with vaping. There literally is a flavor for everyone.
Okay, I wanted to open it up for other people. Jed, you raise your hand.
Yeah. Thanks, Brandon. That was fascinating talk, and you covered a whole range of translational levels of research. So congratulations on that, and thought-provoking. I had a couple of comments and then one question. Although there's really a lot of directions would be interesting to discuss. But in terms of comments, you mentioned, and I would strongly encourage you to follow through on the PK analysis of the vaping chain, because with an aerosol like e-cigarette vapor that's kind of spewing out in the chamber, one can imagine all kinds of things that could go on with a mouse in terms of deposition largely in the nasal passages, and what's the PK of nasal absorption, getting on the fur and being licked, which would then lead to swallowed nicotine, which would become cocaine. So all kinds of questions, and in particular, since menthol and perhaps some other flavorings are known to attenuate the irritation of nicotine. I mean, that's why on the human side, the Nicotrol nicotine vapor inhaler, which is a smoking cessation product, deliberately incorporates some menthol, is to reduce the irritancy of the nicotine base vapor. So some of the effects can be, if an animal can tolerate the irritation more because of an irritation attenuating flavor, that could be part of it. But learning what the exact PK is and equating for that will certainly be important. And you mentioned you're going to do that, but I just wanted to encourage how important that is. And in terms of concentrations, the other thing is really important is, I know in some of the menthol literature, I've seen posters and papers where very physiological concentrations of menthol have been used in various studies. Mm-hmm. So I wanted to also throw in the cautionary note that when you're applying a flavorant to to individual neurons and getting effects to really how important it is to really relate that to what let's say a human or an animal in your model, behavioral model, would actually be taking in and what would be reaching the brain, just to make sure that we're not like 10, 100 times higher concentration, because then we could be chasing a direction that is an interesting phenomenon, but may or may not relate to things, because usually flavorants are present in very small concentrations in cigarettes or foods. So that's good to do. My question is just, I didn't quite follow how the DHBA, DH beta E, in one paradigm, it looked like it reduced the preference or self-administration rather of the nicotine plus flavorant down to the flavorant alone. But in another, it looked like it wiped out everything, and I didn't quite catch the difference in what you might think is the relevant procedural difference, where it obliterated the response versus just taking off the nicotinic portion of and leaving the flavorant reinforced thing. If you could kind of run that by us again, I'd appreciate that.
Sure. Yeah. So that's a good question. It's one of the things that highlights one of the problems we ran into with using the commercial e-liquid. So the first thing I'll say is with the second set of studies, we basically could exactly control the nicotine concentration, the flavorant concentration, and then the number of flavorants. So in this case, we would use nicotine. For green apple, we would use one green apple flavor. And so at the time, most of our data was with farnesol. It was basically nicotine plus farnesol, or nicotine plus menthol in the menthol case. So for example, the menthol bottle that we used that was commercial that basically got us the highest response we've ever seen, it was nicotine. It was labeled as 6 milligrams per milliliter. That it actually was 6, but instead of having just menthol, it had so 3 other chemical compounds, so hexyl acetate, ethyl acetate, which are also used in a lot of green apple flavors, but then it also had a vanilla flavorant, and I can't remember exactly which one. And so right now we haven't done any studies on vanilla flavors. One of the things I'm expecting is that since menthol, so I showed those papers where it was published that they interacted with nicotinic receptors, but then menthol has also been shown to work with 5-HT3 and GABA receptors. So some of the other chemical flavorants are similar in structure to menthol, and some of them are vastly different. And so one of the things I'm suspecting is that with these commercial e-liquids that I was using in that previous set of experiments, that there were some other chemicals that were present that may have accounted for the additional behavior. But then it also just could have been just the application of DH beta E. So basically we're doing an intraperitoneal injection. And then, one of the things that is definitely true that if you have a bad injection, you're going to have a different pharmacokinetic profile. I would like to say that's not an issue because we've been doing IP injections for years, and hopefully we're very consistent. So I really think it may be those chemicals, and that's another area to follow up on, is if that was true and if that's contributing to behavior, that's something we have to investigate and to see what's driving the behavior in that sense.
Great. Are there any other questions directly on there?
Hi, Brandon. This is Saira. Can you hear me?
I can hear you.
Amazing presentation, Brandon. So to follow up on Dr. Rowe's question, if vanillin or other chemicals are having effects on your response, is it like a very menthol specific, or is it like because as farnesol has direct effect on nicotinic receptor currents, do you think like there are other flavors which are not just menthol or farnesol having direct effect on the nicotinic currents? And the other question is like the sex differences. What do you think is causing these sex differences? Is it the nicotinic receptor numbers, or is different in these males versus females, or what else do you think is happening to see that sex differences?
Yeah, so when it comes to the sex differences, I think it's an issue of sensitivity, because one of the things, now we're in the era of sex as a biological variable, but with that said, if you go back into the literature, you'll notice that there's not a lot of sex-specific studies with mice in the nicotine field. And, if you look for, what's the CPP dose response in a female mouse, a female, specifically C57. And I think there's one group that has done that, and I'm not sure if it's been published. And so when we've done our own dose response in CPP, we've noticed that the female mice are a little bit more sensitive. So I think it's really their inverted U is just shifted in a different direction. And we have planned to go into the route of doing a more full dose response to look at the difference in sensitivity. But one of the issues is that, so one thing that happens with the vaping industry is things change very fast. And so at the very beginning, we thought, oh, farnesol and farnesene, these are very prominent flavors. Well, they're very prominent in perfumery and different types of fragrances. But when it comes to vaping products, most of the green apple flavors are actually using methyl butyl acetate, a completely different flavor. And so we basically have had to make the decision, okay, we've had some really interesting results with farnesol and farnesene, but if they're not in most of the green apple vaping flavor e-liquids, then we probably need to go spend more attention or spend more time with methyl butyl acetate. So we've recently shifted gears and we're trying to catch up with basically this particular green apple flavorant, because every analytical chemistry report I've seen, that's been what's like the primary ingredient for green apple flavors. So that's the sex-specific, well, that's the current answer I have for the sex-specific question. So when it comes to the diversity of the flavors and their impact on nicotinic receptors, so there is a poster many, many, many years ago at a tobacco regulatory science meeting, and there is a guy whose name I'm forgetting, but he presented a high throughput screen using an oocyte system with, I think it was up to 50 chemical flavorants and their impact on nicotinic receptors. And 45 of them, it was like 95% of them, were non-competitive inhibitors of alpha-4 beta-2, alpha-3 beta-4. Some of them affected alpha-7 receptors. And so there's a lot of evidence that a lot of these flavors could do something. But my caveat to that study was they were also using very high concentrations. So similar to the non-competitive antagonist studies with menthol, those IC50s were like 30 micromolar. So when it comes to effects in the brain, that's way higher. So as Dr. Rose was saying, you have to think, what's smoking relevant? So we've done a lot of studies looking at nanomolar concentrations, because we know that the concentrations are going to be low. So we basically shoot for a low concentration that we know will be relevant. And that's where we've kind of like started. And so right now, because I'm I guess you can call me an offspring of Henry Lester, a lot of my side interest is intracellular mechanisms. So we do a lot of these trafficking studies on the side. And we've been building up the portfolio of what are these flavors doing. That's something I didn't talk about, but a lot of them are impacting just the steady trafficking of nicotinic receptors. They're increasing insertion of nicotinic receptors, but they're also doing it in a way that the stoichiometry has changed. So that's one of the things that we're working on that I didn't have a chance to look at, but it's all at nanomolar concentrations.